Hi just a second. Let me rejoin again, maybe. Hi, I guess everyone can hear me. If not, please let me know. So, due to some internet issues, I had to like reschedule this class. I guess like there will be much less participants in this class. But welcome to the problem solving session of week 5 of the course titled as Semiconductor Devices Circuits. As all of you know that I take these sessions, and so my name is Shomnath Bhattacharjee. I am currently pursuing my PhD in the Department of Electrical Engineering, IIT Jodhpur, and I am working on organic flexible transistors for neuromorphic computing. And from the next class onwards, like we'll take the session on like every Sunday from 7 to 9. That is the like the basic class schedule. For this one, we had to reschedule it. So this is the basic course layout. And like the last week, we have learned about the RG recombination, that is the recombination generation, different cases and those things, charge transport and the continuity equation. And this week we'll start with this metal semiconductor junctions, that is the junction between two different materials, that is the metal semiconductor or semiconductor, this kind of a thing, and that would be our main focus. So the main three topics we'll learn today is these three things, that is the different types of junctions, electron affinity and work functions, and Schottky and ohmic contacts. So before we start today's session, so like in the last session I have given a problem to solve you guys. If any one of you has already solved it, please let me know. Otherwise, I'll like give the solution first, and then we'll start with today's session. Has anyone done this? If not, I'll give the solution, and then we'll start with today's session. So first, I'll recall you with the problem. What was it, and what was the main aim of this solution? So a semiconductor is in thermal equilibrium. So we have a donor concentration that was varying, that is the NDX. So we can write NDX in naught. At the initial stage, it was in naught, e to the power of minus 10 of x. And we knew that the range of x was from 0 to zero point 0.1 m. So N naught was a constant, the initial constant, and we need to find the electric field at temperature 300 Kelvin. So, sorry. So, as the semiconductor is in thermal equilibrium, total current needs to be zero. So, as it is in thermal equilibrium, the total current needs to be zero. And based on this fact, we know that first, let me write this. So, what is total current? Total current is the current by drift and current by diffusion. So these are the separate terms. So we know that it is 0. So from this we can write q n mu n e plus q dn dn dx, that is equals to 0. So based on this we can write as q n sorry. So first to let you know, so this n is nothing but this. So we'll just like put the values here. So q mu n and not e to the power of minus 10 of x into e plus q dn minus 10 and not e minus 10x, that is equals to 0. So we can write it as like this: mu n e plus, or sorry, minus 10 tn equals to 0. And from this we can write it as e is nothing but 10 tn by mu n. So this was the basic case. And from this, sorry, from this we can write, as we know, that dn assumes the value of kt by q into mu n. And so from this we can write it as like this. So dn by mu n, we know that is 26 millivolts. Okay. From this, so we know the value of dn by mu n, and so we can directly get the value of, that is 10 multiplied by 26. We can write as it is in millivolts, so we have to write it like this: volt per m, or 0.26 volt per m. So we need to find the electric field at T 300 Kelvin temperature, and so we get the electric field as 0.26 volt per meter. So this was the problem I have given to solve, because we didn't have enough time to complete within the session. So we'll start with today's session with this. So like for today's class, what's the main issue is that there were several derivations, and from the next class onwards as well, we'll have so much derivations. So I won't go towards those kind of derivations. I'll talk about the basics of the phenomena and the basic things actually, but I won't go in depth derivations and those things, because you guys can like recheck the videos multiple times and you can get the derivations and everything. So what I'll do, I'll just go through the concepts, and like in this session we'll go through the band bending and those kind of a things, because those are the most important topics to like understand. If anyone have any question on those kind of derivations, then please let me know, and then we can discuss it on the next class or something. So so the basic recap of like today's class would be like, we'll start with junctions. So there are like seven kind of junctions. Let me write it down, and then we'll start. So the first things we learned this week was junctions. So there are several kind of junctions. So there can be a junction, or metal metal junction. There can be a MS junction, that is a junction where there is a metal and also a semiconductor. In most of the cases these are like n type or p type dope. Just a second, sorry. Yeah. And the third one is semiconductor junction. So these are three kind of a junctions possible, and based on this junction, based on several factors, we have two kind of a context, that is the Schottky and the ohmic context. First, we'll learn about these junctions, and then we'll move to those things. So the first thing we learned in this case was the concept of electron affinity. So what is electron affinity? Electron affinity is nothing but xi qs. So this term is called the electron affinity, which is nothing but the difference or the separation between the vacuum level of an semiconductor with the conduction band of an semiconductor. So if we have a, let's say we have a semiconductor like this, so this is the E vacuum level, this is the EC level, let's say this is the EF, and this is the EV, and we also have this, that is EFI, or the intrinsic Fermi level. So in this case, so just a second. So this separation is termed as the electron affinity. And what we know about this, as this is a constant one, so the conduction band, the energy of the conduction band doesn't changes, and also the vacuum doesn't changes. So this value is nothing but a constant term. Sorry. Now we have another concept that is called the work function. So what is the work function? Work function is nothing but Q psi s. So this is termed or defined as E vacuum minus EF. So the difference between the vacuum level with the, just a second, the vacuum level with the Fermi level. So this distance is termed as the work function. Now the problem with this is, just a second, right? So now the problem with this one is that this term, the Fermi level, based on the doping concentration and many other factors as well, this changes. So this is variable, due to which this term is also variable. So in case of semiconductor, the electron affinity is a constant term, but the work function is not a constant term. Now, so if we can define it for the metals as well. So what would have happened that for a metal, if this is, let's say, the vacuum energy level, and this is the Fermi level, EF. So in case of metals, so let me write it down. This is for metal and this is for semiconductor. Now, in case of metals, this is the work function for a metal. So this doesn't changes because the Fermi level for a metal is constant. So for a metal, we can write it down as like this: Q psi m as E vacuum minus EF. Now for this case, so this is constant for metals and this is also constant for metals. So we can say this is also constant for metals. So we get to know that the work function for a metal is constant term, and also the electron affinity for a semiconductor is a constant term. And based on these factors, there is a phenomena which is called the band bending. So after that, we have learned this week the concept of band bending. So what is band bending? So let me just draw it down. So if this is a vacuum energy level, and if this is the Fermi level, so this is the metal and this is the work function, this is constant. And now if we have a semiconductor, let's say like this is the EC, this is the level EF, and this is EV. So let me just draw it like this. Okay, so this one is EF. Now and for this case, this is also constant. Now, so if we make a like a contact for a metal with a metal, what happens that if a metal has a work function higher than that, they will align anyways. Okay. In case of a metal and a semiconductor, so like metal semiconductor junction, what happens? At thermal equilibrium, the Fermi levels align with the Fermi level for the metal and Fermi level for the semiconductor will align. So they will look like this. So let's say we have a common Fermi level, and based on this, we have a E vacuum. As we know, this is a constant term. Due to this alignment, what happens? First, let me just draw it like this. So up to this is the metal part, and after this is the semiconductor part. Now, what happens is that the Fermi level and the EC, that is the difference between Fermi level and the conduction band, they are constant for a certain level of doping. So based on that, we can draw this. So this is EC, and we also know that the difference between the EC and EV, that is the valence band and the conduction band, it is also fixed. So we can draw the EV, and based on that, we can also draw this. That is the vacuum level. As we know, this difference is also constant. That is the conduction band and the vacuum level. So based on this, there is a phenomena of bending that is like this. So there is a what do I say, like there is a bending in the band in case of semiconductors, not in the metals. Metal bands remain same, exact same, but there are slight bend in the semiconducting layer. So based on that, we have, as the distance between the EVAC and the EC is constant everywhere. So based on this, so like the bending will be also same for this as well. Now to clearly understand this, so we know this is constant, and the same thing is here as well. Wherever there is a bending in the band, the vacuum level also bends there for the semiconducting layer. And also we know that there's a, this distance is Eg, that is the band gap. This is also same for this case as well. So this phenomena, this is not a physical phenomena, but to learn the inner concepts of these kind of a junctions, we need to learn this. So this is also this is also a empirical kind of a phenomena that is called as the band bending here. And also so this is for a N type, obviously N type semiconductor, and this is for a metal. Okay. So this side is a metal one, and the right side is the N-type semiconducting one. Now here, what we have is that, and here with here, there is a same distance as well. So this is nothing but Q psi m, that is the work function. This is nothing but Q psi s, that is the electron affinity, and this is Eg, that is the band gap. Okay. Now what happens is that, sorry, this is not Q psi s. This one is Q psi s. So this is Q psi s, and this one is Q psi s. So this Q psi s is variable, whereas the Q psi s is constant over whole region and everything. So this phenomenon is called as the band bending. Let me rewrite it. Okay. Now the same thing will happen in case of P-type materials as well. So let me just draw it fast. So this is the same kind of a structure, or the same thing will happen for the p type as well. So I am just going through that. So like we can introduce the semiconductor semiconductor junction. So this is one of the most important thing, that is the PN type junction. So the most common one is the PN junction. So just a second. PN junction. Let's have a semiconductor like this. That is, we have this here. That is the E vacuum. We have the EC. We have the EV. If we are making this a P type, then the Fermi level will would be here. Similarly, let's draw another one. So this is also EC. This is also E vacuum. This is EV. But in this case, the Fermi level would be here. So this is EF for the N type, and this is EF for the P type. Now, if we are making the semiconductor junction, what would happen is that first we need to align the EF. Then based on that, we need to draw the EC. So in the first case, the EC would be higher, as it was higher in this case. And for this case, the EC would be lower here. And as the EG of both the materials are same, so same after making the junction, not same for both the materials. So this would be here, and this would be kind of a here. And based on that there would be like the vacuum level. So let's say if vacuum level was here, based on that the vacuum level would be here. Now, so there would be the band bending phenomena here. There should be a bending of like this. So I am drawing like this, but it should be a gradual, like kind of a decrease. So this is P side and this is the N side. So based on this, there would be a junction forming between a P and a N type semiconductor, as the EF, that is the Fermi level, aligns in both the cases. So this is the EC for the P type. This is the EC for the N type. This is the E vacuum. This is also the E vacuum. This is EV. This is also EV. So this is like a junction that is between two semiconductors. And after that we have derived so many things after this. So I am just skipping those things. If anyone have any questions, you can ask me after, like after the class. Like I would give some time for that. And now we have learned about the contacts. So there were different types of contacts. So when there is a junction, there are like there is the basic interconnection between these two materials. That is the that can be either metal or metal semiconductor or semiconductor. And based on their connection, there is two types of contacts forming. So the first one is the ohmic contact. So in ohmic contact, the basic thing is that psi m is always less than psi s. So here from this you can like get that the work function of the metal is less than the work function of the electron affinity of the let's say the work function of the semiconductor. So the work function of the metal is less than the work function of the semiconductor. And the second one is Schottky contact. In this case, the work function of semiconductor is higher than the work function of the metal. No, no, no. I have written the same thing. Sorry. The work function of the metal should be higher than the work function of the semiconductor. So in most of the cases, there is the this kind of a contact forming. So after that, what we have learned that for each of the cases we have derived the results. I am not going through the derivations. After that, we have learned that based on if we are introducing a kind of a bias, like let's say a reverse bias or a forward bias. So based on bias voltage change in the contact parameters. So based on these kind of a bias, let's say the reverse bias or the forward bias, there would be several changes in the contact parameters. We have also derived those kind of things. After that, we have learned the most important thing, that is the current voltage characteristics. So why is it important? Because for any kind of a MOSFET or a BJT or those kind of a things, this is one of the most important characteristics. So we are just going through this kind of a characteristics like the current voltage characteristics from this. Like there were several phenomena for a short key case. So there were like diffusion, there was like a thermionic emission and those things as well, and also tunneling. So these were for short key cases. So based on this, we have learned how these devices behave based on different voltage application to them, and we have got this current and voltage characteristics. Why is it most important? Because from this we have gotten several key parameters. Those are like the current density. So for any kind of a MOSFET, it is very important because from this kind of a current density, you know that like how this device behaves based on the current and voltage characteristics. Like there are some devices called the MOS caps, so MOS capacitors, and from that we get the value of C, that is the C ox in most of the cases, that is the oxide capacitance thickness. In this case, we have learned the capacitance per unit area. So this is very important because in like MOS transistor equations and everything, we need to know what is the Cox value. We need to know what is the current density values, because to understand the device phenomena completely, we need these parameters. So from these kind of a contacts, like a PN contact or even a metal and a semiconductor contact, we need to get this kind of values. And afterwards, when we learn about the MOS caps or the BJTs or the MOSFETs, we need to understand why it was that kind of important to start with these similar like similar kind of a junctions, and after that there would be several junctions like three, four, even five junctions as well. So in those cases, it would be very important to learn about like each single junction separately. And after that, we have learned about the uh, no, this was for this week's case. And also there was a like note that a Schottky contact is known as the rectifying contact as well. So based on this factor, we also have the Schottky diode as well. That is a basic kind of a diode, and like because these Schottky contacts, what do I say, like they work similarly to an like a diode circuit. So based on that, we can say that they can be called as the rectifying contact or the rectifying diode kind of a thing. So this was the basic recap of this. So I haven't gone into like in-depth details because like most of them were derivations. And if anyone have any questions on that, you can ask me. And also based on these things, if anyone have any questions, otherwise we'll move towards to the problems and everything. So if there are no questions, we start with the, yeah, metal with metal. Yeah, sure. So here, just a second. Yes. So this was because the metal with a metal is kind of a very easy thing. So that's why we are not concerned about those things. So as we are learning about the semiconductors, that's why I have like skipped that part. But I'll just explain here. Maybe just a second. So in case of a metal semiconductor junction, what happens is the main phenomena that is called the band bending. So if a metal contact is here, let me draw it somewhere. Let me start it here maybe. So so if we have a metal contact, what would happen is that we have a E vacuum for a metal, we have a EC, and based on that we would have these thing as well. Wait a second. Was I writing wrong? No. This time I have written wrong. So based on this metal has a lesser work function, that is the QM for this case. Psi m for this case is smaller, let's say 1. For this case, it's higher. So this is the junction portion. So what would happen if there are, let's say, electrons here? They will just jump here. That's it. There would be no kind of a bending because, like, what happens in the semiconductor is that the Fermi level aligns, and based on that there are the other bands which are getting bended. But in this case, as there are no other bands to like bend there, the the what do I say, the the higher work function metal would attract the electrons from the lower work function electron at lower work function metal. That is, let's say this is as the metal 1, this is metal 2. So electron from the first one will drop to the second one. So in this case as well, let me just go here. What happens is that, no, let me draw it here just for this case. So if we have a slope like this, let's say we have a slope like this, electron behaves like small marbles. So electron drops through this slope and they get accumulated here. And the holes are like balloons. So what will happen? The holes from here would travel here and they can't pass this barrier, so they are just below there and they will accumulate here. So this is the basic phenomena there. In case of metals, what would happen that there are huge number of mobile electrons there, and these electrons will flow, and based on that there would be this contact forming, and this kind of a thing is called the work function difference. So based on this kind of a thing, we tend to avoid the work function difference. That is the we say that the work function mismatch. So we tend to avoid those kind of things, and we in general for device fabrication and those things we try to get the work function very near to each other. So in case of semiconductors, we if we are using a semiconductor with a metal in like realistic cases where we are fabricating the device and everything, so we check the the metal the work function with the the semiconductor band gap. So based on that we check if those are like in the nearby region, and based on that we can fabricate the devices. We tend to avoid this kind of a work function mismatch and these things. So if anyone have any other questions, let me know. Let me me write it like so. These are electrons, these are holes. So they resemble the characteristics of balloons, whereas these are like marbles, or let's say balls of some kind. Okay. So if there are no questions, just a second. I'll just get back within 1 minute. Yeah. So let's start with the problems first. So for the first problem, like for this week, what we'll ask is happening. Yeah. So let's assume an arbitrary metal that forms a Schottky contact with an N-type semiconductor. So how does the Schottky barrier height vary if the doping in the semiconductor decreases? So we have several options here. The first option is it increases. Second option is it decreases. Third, it remains unchanged. And fourth, it becomes zero. So give me the answer and also the reasoning why it is happening like this. So the question is that we have a metal semiconductor junction, that is a Schottky contact. There's a Schottky contact happening, and so like if we are decreasing the semiconductor doping, based on that, what is the shift in this the Schottky barrier height, the barrier height? Will it increase or decrease or remains unchanged or like it becomes zero? Trying to answer this, and also I need some kind of a explanation about this, why it's happening and everything. And if you can give some kind of a let's say equation to like justify your answer, that would be better as well. So based on decrease, okay. Others? decrease. Okay. So, like any one of you can explain why you think that it decreases. So, based on the doping concentration, like it depends, and like based on the change in doping concentration, like if we are increasing the doping concentration, let's say the barrier height will increase, and if we are decreasing the doping concentration, the barrier height will decrease. So, why is it? Uh, it will decrease because it doesn't depend on doping. I'm not sure. Like, can you like write it down or something like this? Or you can turn on your mic and just say it. So my question is that if it doesn't depend on the doping, so how will it decrease then? So answer from both of you is that if we are increasing the semiconductor doping, height should increase as well. And if we are decreasing it, height should decrease as well, right? Based on the number of electrons. Okay. So you are saying if we are increasing the n-type doping, there would be more electrons and the height would also decrease. So let me explain this. So this is actually wrong because the Schottky barrier height is nothing but Q psi b. So this is the Schottky barrier height. So for a metal and a semiconductor case and those things. So we know that Q psi b is nothing but Q psi m minus chi of S for the semiconductor. So the difference between the what do I say, like the difference between the work function of the metal, that is let me write it down maybe. So this is metal work function, and this is the electron affinity of the n-type semiconductor. Now from this we know that the metal work function is a constant term, right? So it doesn't depend on the number of doping or those kind of a thing because there is no doping anyways in the metal. So this is a constant term for the metal, and the electron affinity is also a constant term as I have already stated, right? So based on the doping, it doesn't depend it doesn't depend. So we can say that Q psi b should also be a constant. So the Q psi b should also be a constant. So based on that, the answer would be this one. It remains unchanged. So if we are increasing the doping, if we are decreasing the doping, anything based on this, based on the doping concentration and those kind of a things, the Schottky barrier height would always remain same. Are there any questions? If not, we'll move to the next one. So let's move with these kind of a questions first, at least two or three, and then we'll move to the numericals. So in an arbitrary metal, it is deposited on a lightly doped n-type semiconductor. So there is a metal semiconductor case again. Now we know that the work function of the metal is much higher than the work function of the semiconductor. Now we know that psi m is greater than psi s. Now, which one of the following steps will make the contact an ohmic one? The first options are doping the semiconductor heavily, degenerately with n-type impurity near contact region. Second case is doping the semiconductor heavily, also degenerately, with the p-type impurity far away, doping the semiconductor lightly with a p-type impurity near the contact region, and no further processes required as it is already an ohmic contact. So which one is correct? So from the question we know that, we have a metal here in this side. Just below that there is a lightly doped n-type semiconductor, but lightly doped. So on top of that we have the metal. So what should we do to make it like a Schottky contact? Doping semiconductor lightly. Okay. Others? So what would happen if we dope it near the contact region with p-type impurity, likely p-type impurity? It would kind of make it to an intrinsic semiconductor, and based on that metal and those kind of a junction. So there was another thing that first we need to eliminate one, right? So for that, what we know that the metal work function is much higher than the semiconductor work function. So we know that, I guess we can write it with this. So we know that psi m is greater than psi s. So it is a Schottky contact. So the fourth one is obviously wrong, and lightly doping is obviously wrong because it would make it a neutral one. Yes, the correct one is the first one, not the second one as well. Because making it if we are doping it far away from the contact region, it won't affect the, yes, right. So because of n type of semiconductor, obviously, but based not only based on that. So if we are doping it just far away from this, so let's say we are doping this portion, so this won't have any effect on the contact region as well. So it doesn't have any kind of effect. So based on that, we can't dope it with p-type impurity, as it is already a lightly doped n-type impurity, n-type semiconductor. If we are doping it with a much higher concentration of the dopants and everything, it would make a ohmic contact over time. So the basic thing, let me write it down, I guess. So in case of a n-type semiconductor, so the as we know, this is a Schottky contact by nature and everything. So to make it an ohmic contact, what what do we need? So we need to increase the semiconductor the semiconductor work function, right? So we need to increase this one. So semiconductor needs to be heavily doped with the same type of impurity. So as it was a n-type, so we would dope it with n-type here in this case. Now the case is that we need to make it like this, right? So how can we make it like this? By changing the Fermi level, right? So here, let's say, so here's sorry here, right? So the work function is nothing but the difference between the E vacuum and EF. So our main aim would be to increase the value of EF higher, so that we can, based on that, we can make the value of this higher. So for making the Fermi level go higher, we need more doping. So it is a correct answer. Now we'll move to the question number 3. Now, in a certain Schottky contact, a negative bias is applied on the metal with respect to the n-type semiconductor. Okay, so we are applying a negative voltage to the metal portion with respect to the semiconductor, and so based on this, what would happen to the compared to the equilibrium state the magnitude of the peak electric field will decrease or sorry will increase or decrease, and the width of the depletion region will increase or decrease. So the question is that we have a Schottky barrier, which is the connection between a metal and a n-type semiconductor. Right now we are applying the negative bias on the metal with respect to the negative negative side is the n-type semiconducting layer, and based on the equilibrium state, now what will be the change in the peak electric field? Will it increase or decrease? And what what would be the change in the depth of the depletion region, the width of the depletion region, that is, will it increase or decrease? Give me the answers, and also tell me why is it happening. Depletion width is xt, and the peak electric field is psi max. So what would happen? Increase which one? The first one or the second one? Or, yes, you are correct. And what would happen with the electric field? What's happening here with that? Yes, yes, that's correct. The depletion region would increase. This is a correct one. What would happen with the peak electric field? We know that the equation of the depletion width is xt root over 2 of epsilon s psi of minus VA. So if the VA is the applied bias voltage, divided by Q of NT. So this is the case. Sorry. So at thermal equilibrium, VA was zero. Now, whenever we are just applying a negative bias, so let's say at if we are applying a negative bias, let's write it as like this. So if the bias value is VR, so like this. So let's say it as a constant because of the same terminal plus and minus. So you are saying that the depletion width will decrease. So as I was saying here, so as the value of this is increasing, right? Because it is plus VR. So if we can write it like this, 2 of epsilon s psi of Vi plus VR divided by Q and D. And at this case, it was XD as root over of 2 epsilon s psi Vi divided by Q and D. So obviously it's increasing, right? So if this was the first one, so it is increasing. As we have a negative bias, if it wasn't like a positive bias, so it would have like a minus term here, minus VA, let's say. So if that was, let's say, the positive bias or like a forward bias, so that would have mean like it would have been like this. So for a forward case, so in that case, it would have decreased. Now, similarly, so what would happen in this case? Now we know that, sorry, so psi max is nothing but Q N D xt by epsilon s. Now, what do you think? What will happen? So as xd is increasing, this has to increase as well, right? Whenever xd is decreasing, this value will decrease as well. So based on the as like you have xd here, right? So based on this, this is nothing but, so based on the increase in xd, it will increase. So in this case, as we are giving it to a like a negative bias, based on that, both the terms will increase. So this is the correct answer. So we'll move on to the numerical problems. If anyone have any question on this, so let me know. Let me write it down with this ink actually. It should be in this. So we'll move on to the numerical problems. So we have a chromium and N-type silicon metal semiconductor junction. Now we know that the semiconductor is doped with impurities, that is 10 to the power 17 per cc. Now we have to calculate the Schottky barrier height in EV and also the built-in potential at T equals to 300 Kelvin. And there are few like already given terms as well. So we know that the work function of chromium is 4.5 eV. The work function of let's sorry the electron affinity of silicon is 4.05 eV. The band gap of silicon is 1.12 ev. The relative permittivity of silicon is 11.9. Value of Nc for silicon is 2.82 into 10 to the power 19 per cc, and value of Nv is 1.83 into 10 to the power 19 per cc. Now calculate the value of the Schottky barrier height and the built-in potential. Let's have like 3-4 minutes and try to solve this equation. So has anyone able to solve this? So I'll give the solution for this, and for the next one, try to do it in the same way, I guess. So the Schottky barrier height is nothing but q psi b, right? So that is the difference between q psi m minus psi s. So what is that? So the work function is written as 4.5 ev here. We have this value of this, and the electron affinity we also have here. So the values are like this. So this is nothing but 0.45 ev. Now we need to know what is the built-in potential. So the value of built-in potential is psi bi. That is nothing but the difference between psi b minus psi f. Okay. So now we have the value of psi b minus the difference between the so here from this, let's say we have this, right? So here we have the value of q psi b. So obviously from this we can write it like this: psi b is nothing but sorry, 0.45 volts. Just the e portion gets like eliminated. So from this we can write it as like the psi f value we can calculate sorry, the psi f value we can calculate obviously. So from that we can write it like this: kt by q ln of nc by nd. Now we can just put all the values here. So from this what we get is like 0.45 volts minus kt by q is 0.026 and ln by 2.82, as we have the value of nc here. So 2.82 into 10 to the power of 19 per cc divided by nd. So nd is here, that is 10 to the power 17. So just let me do it here. So what we have is 2.82 into 100, right? So 282. So ln of 282 is this. The value is 0.45 minus 0.026 multiplied by 5.6419 multiplied with 0.026, that is 0.45 minus 0.146, or let's say 147. So the value is 0.147. 0.45 minus 0.147. Sorry, 0.45 minus 0.147. The value is 0.303, or we can write it as like 0.3, but in volts, like yes, 0.30. Okay, so like based on the the correction, so I have got the value of 0.306, so that's why I am writing it like this. So the value is this. Now just we'll change the solution, like this, change the problem with this. So on question number 5, just repeat the problem. Repeat the problem and just assume, while assuming the dopants were p type. So in the previous case it was n type, and just repeat it if the like if all the things were in like p type. So the nd remains same and everything remains same and everything is same, but just change it to the p type case. I'm showing this page because there are like the formulas written and everything. Where would be the basic change here? Just find it out and just you will get the answer. Take a minute or two, I guess. So I'll give some hints. So there last time it was ND for question number 4, and for question number 5 it would be Na, right? And it was 10 to the power 17 per cc. Apart from that, so like first try to get the built-in potential. So the built-in potential is QBI equals to QB minus QF. It would remain the same, exact same. But what will happen is that psi BI equals to psi B minus psi F. Now there would be change in the psi B and also the psi F, because like if we are writing it like this, KT by Q ln of NV by NF. So right now NA and ND were both same for both the questions. So that's why the lower term will remain the same. But in this case, what would happen is that there would be a change in the this value. So the change in NV value, obviously it was previously used as 2.8 into 10 to the power 19, but this time it would be 1.8 into 10 to the power 19. Apart from that, the value of Q psi B is nothing but psi of S plus the band gap minus the work function. So it is nothing but 4.05 plus 1.12 minus 4.5 in EV. So it is nothing but 0.67 EV. Now, based on this, we can write it as like this, 0.67 volts, and we can just put it directly here. So 0.67 volts minus 0.026 as in case of the last one. So this would be nothing but 10 to the power 19 divided by 10 to the power 17. So let's calculate it again. It is 183, right? ln of 183 is 0.67 minus 0.026 multiplied by 5.209 into 26. So it would be 0.67 minus 0.1354. So it is 0.5345, but in volts. So let's write it like this, 0.535 volts. Okay. So the first answer is this, and the second answer is this. Now, what would like we would like to do is that it was question number 6. So let's do one thing. Let's like just apply a bias onto this. So applying a 5 volts reverse bias. What would be values of first one is depletion width. So if we are applying a 5 volts reverse bias, what would happen with the depletion width? Second, what will be the value of electric field at the metal semiconductor junction? C is what is the potential drop across the so junction, and finally D is what is the capacitance per unit area in nanofarad per centimeter square. So based on this case, what we are doing is right now is we are applying a reverse bias of 5 volts. That is a minus 5 volts. We are applying it here. And based on that, we need to know what is the depletion width, what is the capacitance per unit area, what is the potential drop across the junction, and also what is the electric field. So we have already used this equations here. So we already know the equation of depletion width, and we also know the peak electric field equation. Try to solve this. Take 2 3 minutes. I guess it's the most easier one because just you have to put the right values here. So was anyone able to solve this? Solve any of the parts. So if not, the most easiest one is the depletion width, obviously. So depletion width is xd, which is nothing but E of epsilon s psi of bi minus Va, that is the applied voltage, Q of Nd. Now, if we put all the values here, this would be 2 into 11.9 into 8.85, 4 into 10 to the power minus 14 into 0.3. So the zero point 0.3 value is directly from here because at number 4 question we have just done this. So 0.3. Otherwise we can also use 0.304 or 303, but I don't think it would have any like much higher effect or something. And it would be plus because it is a reverse bias. That's why minus of minus 5, and this one is 1.16 to the power of minus 19 multiplied by 10 to the power of 17. Let's just put the values here. The values would be 8.854 multiplied by 0.5, 5.3, sorry, 5.3 multiplied by 11.9 multiplied by 2 divided by 1.6. So this is like this. So root over of the value is nothing but 26.4. And now we just calculate these values. So this is minus 2. That is minus 2 10 to the power of minus 14 minus 2. So 10 to the power of 14 minus 2. Sorry, 10 to the power of 16 minus 2. That is multiplied by 10 to the power of minus 8 meters. Now we can write it as like 26.4 10 to the power minus 2 micrometers, or 0.264 micrometers. Now, if we derive the second one, that is the electric field. So, electric field at the metal semiconductor junction, that is at x0. So, the value of electric field at x equals to 0 is nothing but Q of Nd xt divided by epsilon s. So the values would be 1.6 into 10 to the power of minus 19 multiplied by 10 to the power of 17 multiplied by 0.64 into 10 to the power of minus 6, right? 11.9 multiplied by 8.854 multiplied by 10 to the power of minus 40. So this is nothing but 1.6 multiplied by 0.264 divided by 11.9 divided by 8. I have to recalculate it again. So 10 to the power 16, 0.264 divided by 11.9 divided by 8.854. So what we get is the value of this. So this is 0.004, and there are multiple zeros. Just remove those. So we have 10 to the minus 2, 10 to the minus 8 divided by 10 to the power 14. So the values are 10 to the power minus 14, and so just write it down. This 6, so minus 8. That is 10 to the power of 10 to the power of 6, right? Or am I wrong? Yes, so the values are this. So let's write it like this. So 4 multiplied by 10 to the power of 3 volt per meter. Or if we are gonna convert it to centimeter, it would be 4 into 10 to the power of 5 volt per centimeter. Okay. Now the C was potential drop. So built-in potential, or sorry, BI was found to be 0.3 volts, nearly 0.3 volts. So and we also have the applied potential, that was VA, that was minus 5 volts. So the potential drop would be psi VI minus of VA. So this would be 5.3 volts. And the last part is capacitance per unit area. So if it's we can write it as like Ci or Cj. So based on that, epsilon is divided by x of d. So it is nothing but this 8.854 into 10 to the power of minus 14 divided by, what was the value of xt? Xt was 0.0264 multiplied by 10 to the power of minus. So let's write it in centimeter anyways, because we need to convert it to centimeter square. So it should be this, or we can write it like this. So 11.9, 11.9 into 8.854 divided by 0.264. So the value is nothing but 399.1 nanofarad per, not nanofarad, farad 10 to the minus 4 into 10 to the power of minus 10 farad per centimeter square. So it would be 39.91 nanofarad per centimeter square. So this was the case, and let's like do another problem, and we would end today's session after this. So let's take another case where we have a metal semiconductor junction consisting gold with work function of 5.1 eV and n-type silicon with dopant concentration of 10 to the power of 15 per cc. If the metal contact is kept 5 voltage below the semiconductor, what is the electric field in the semiconductor at 1 micrometer distance from the junction at T equals to 300 Kelvin. So it's exactly same as the previous one. So they have mentioned that the metal is 5 voltage below than the semiconductor. So that is also similar to that. That is a minus 5 volt reverse bias. And based on that, we have also have the value of ND. We have also value of the work function and everything. And they have also given few constants. That is the value of NC is 2.82 into 10 to the power of 19 per cc. Electron affinity of silicon is given as 4.05 eV, and relative permittivity of silicon is given as 11.8. So these are the given values based on the previous like problem what we have already solved. That is the we have to so this is for 2.64 into 10 to the minus 5. Yes, you have got the same answer, right? So based on this, what would be the value of, just a second, what would be the value of this? So we have already used those previous. Sorry. So based on the previous equations and everything, just try to solve this. So we need to get the value of xi x when x, the value of x is this 1 micrometer. So we have already given that. Try to solve this. Take take I guess 2-3 minutes something. If you like, the same equations will be used here as well. For this one, I'll give the equation, I guess. So I'll just write it down because in the previous one we have already used it. So this is this. So in the previous case, what we had is that the value of x was 0. So just try to just put the values here. Q of n d by epsilon is x minus, and get the value of this as well. Psi pi minus va whole divided by q of nd, and based on this you can get all the values. And also for this we have to first get the value of this. So this is nothing but qb minus kt by q ln of nc by nd. I guess yes, these are the equations we have to use, and you have just to put the values here. So anyone was able to solve this, or should I just give the solution? If not, I'll give the solution. Then, so from this, what we can get is the value of this. That is 5.1 volt. 5.1 volt for the like the gold work function, and this would be the electron affinity of silicon. From that, we have the value of this with ln 2.82 10 to the power of 19 divided by 10 to the power of 15, and we get the value of this is about 10 multiplied by 0.026 with the minus of 5.1 with a plus of 4.05. So the value is nearly 78.357 EV, right? Not EV, sorry, my mistake. It would be in volts, because if it would have been if Q psi BI, then it would have been EV. And for this, then we have for X, we have the value of this, right? So 1.6 into 10 to the power of minus 19 multiplied by 10 to the power of 15 whole divided by 11.8 multiplied by 8.854 10 to the power of minus 14. And so let's do one thing. Let's put it as 1 micrometer. Then we'll have the value of this if we are going for the centimeter values. And from this, let's just divide it from here. 2 multiplied by 11.8 multiplied by 8.854 into 10 to the power of minus 14 multiplied by this 0. Just a second. There might be some mistake from my side. So it was calculated as, okay. So this is like this. So let me rewrite it then. So it was 0.78357 volts. Let's write it like this, 0.78 for the time being. So if we are putting it like 0.78 and divided by the value is, no, actually 0. Not 0.78, it would be 5.78 divided by 15 10 to the power 15 multiplied by 10 to the power of minus 19, and this would be inside the bracket. Let's put everything down. So it is 2 into 11.8 multiplied by 8.854 multiplied by 5.78. So into multiplied by 10 to the power of minus 14. So this was the total value. If we are to just, let's calculate it separately. And so the value would be in volt per centimeter, right? 1.6 multiplied by 4 divided by 11.8 divided by 8.854. So this is, so this comes out about 26.7 dot 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 something like this, like this. So the values are like this. There would be like we have to put each of the values and everything. So this would be nearby to this. So if anyone have any questions, please let me know. Otherwise, we'll conclude today's session and we'll meet again on next Sunday, like this Sunday, sorry, this Sunday from 7 to 9. And I'll share the slides and the video recording and everything of the session with you guys as well. So we'll conclude today's session. Thank you for attending this.